Hey, welcome to AP Chemistry with Mrs. Mays. This is podcast 7.2, where we will use periodic trends to predict the types of bonding between atoms. First, let's look at electronegativity. Electronegativity describes the ability of an atom to attract shared electrons to itself. So, it's in a bond, but it's pulling on the electrons and bringing them in. In order for us to measure the electronegativity of an atom, we rely on the Pauling method, where we take some imaginary molecule HX, comparing the atom you're interested in to hydrogen, right? And we calculate the expected bond energy between hydrogen and that particular atom. And we take the average then of the hydrogen energy and the whatever atom you're interested in, X energy, and then divide by 2. We take the average. That's the expected energy. But then after you measure the actual HX, you can see the difference between what it was calculated to be and what it really was in the experiment. That's what we call the electronegativity value, and it gets this sign capital delta, that Greek letter delta that looks like a triangle. That's the symbol we use for electronegativity. And delta is known for almost every element on the periodic table. It gives us relative electronegativities, not absolute values, but relative numbers, like compared to hydrogen, for all of the elements that we know. It tends to increase as you go from left to right on the periodic table. So moving across the row, left to right, the electronegativity values increase, and it decreases as you go from top to bottom. So as you go down a group, of course the top atoms will have the highest electronegativity because they have the least amount of shielding, and then it gets weaker and weaker and weaker as you add more layers of shielding, adding more energy levels. And noble gases aren't discussed. There are no available values of electronegativity for noble gases, because since their configurations of electrons are stable, then they don't draw electrons towards themselves and they don't form bonds. The difference in electronegativity between atoms tells us just how much ionic or polar the bond is going to be. We can measure on a sliding scale how much ionic character a bond has. So if your difference in electronegativity is 0, then that means the bond type would be considered to be perfectly covalent. 0 meaning they're both equally electronegative. Like if I have fluorine bonded with another fluorine, for instance, then their electronegativities are both 4. So I have a 4 minus 4 equals 0. Perfectly covalent. They share evenly because they're like exactly the same thing. An intermediate molecule would be considered polar covalent, and our classic example of polar covalent molecules would be like water, where you have oxygen bonded to hydrogen. Hydrogen has an electronegativity value of 2.1. Oxygen is a 3.5, and so the difference between 3.5 and 2.1 is, that difference is 1.4. So it's not big enough to be considered ionic, but it's certainly not 0. The oxygen is hogging the electrons way more than the hydrogen. But if you had a larger value, we would see an ionic bond. For example, if we have sodium with fluoride, like we would expect a metal and a nonmetal to make an ionic compound, then we would take the electronegativity of fluorine, which is 4, and subtract from that the electronegativity of sodium. When we subtract these two, we get a value of 3.1, which is a really large number. Anything greater than 1.7 is considered to be ionic, so 3.1 certainly meets that criteria. Because once you get to 1.7 in that difference, then that bond is more than 50% ionic in its character, so we just consider it to be ionic. So as we look at this scale here, when it's 0, the covalent character is decreasing as the number, the electronegativity difference increases. The ionic character increases, though, as the difference in electronegativity gets bigger. So it's a sliding scale. And we know that when it's halfway in between, then we have something called a dipole. A molecule that has a center of negative charge and another center of positive charge is considered to be dipolar because it has two poles. In other words, it has what's called a dipole moment. And a dipole moment in physics is an important feature in where that charge is located around the atom or around the molecule. It's kind of like the idea of the center of mass. The center of charge, though, doesn't have to be on an atom necessarily. Like in water, we have our negative end on the oxygen, so I'm going to draw my partial negative here, and then the positive end is sort of on both hydrogens at the same time, which means that it averages out to be somewhere in between. So the dipole moment, the dipole establishes across the center of the atom, and the dipole moment is somewhere in the middle. That's like the center of mass for this molecule, only it's like the center of charge instead. And that's how we determine how these molecules line up in the presence of an electrical field. Earlier we looked at this particular molecule, HF. We always draw that dipole moment with a vector arrow that shows the positive charge with the plus on the arrow itself, and it points from the positive to the negative, just like vectors do in physics when you study electrostatic attractions and electrical fields. So which molecules are going to have a dipole moment? Well, you need to have two things. There's two criteria. First of all, you must have a polar bond. If there's not any polar bond in the molecule, then there's no dipole moment on that molecule. And the second criteria is that the geometry of that molecule must be such that it does not cancel the vectors or the dipole moments in that molecule. So let's look at specifically what we mean. So any two atom molecule with a polar bond will have a dipole moment. It just will, because a two atom molecule lines up in a linear form. If you have three or more atoms, then we have to look at our two considerations. There must be a polar bond. And do you remember the other one? It's about geometry. The geometry can't cancel out those polar bonds, those dipole moments. They all have to stay intact or it won't be a polar molecule at all. So three shapes in particular will cancel out. If you have triatomic linear, or more than three atoms, any polyatomic linear atom could potentially cancel your dipole moments. Planar triangles tend to have dipole moments that can cancel as long as all three atoms that you have here are the same ones, then your dipoles end up canceling out. And then tetrahedral shapes, as long as all your atoms are the same, their vectors for the dipole moments also cancel each other out. Now if I were to replace this with some other atom, say these are all hydrogens and I put chlorine here instead, now I've changed the geometry so that they won't all cancel. We're going to practice this a lot after you've had a chance to draw molecular shapes a little bit. Then we're going to practice predicting whether the bonds are polar or nonpolar, and then we'll look at are the geometries of the molecules going to cancel out to give us polar molecules or nonpolar molecules. Here are some that will not cancel. This bent geometry does not allow for the dipole moments to cancel out. So bent molecules tend to be polar molecules. Trigonal pyramidal geometries do not cancel. Like ammonia is our most famous example of a trigonal pyramidal molecule that is also a polar molecule. So when you're looking to decide, is it an ionic bond or is it a covalent bond, then your important number to decide is this 1.7. If you have 0 to 0.4, then it's considered nonpolar. If it's greater than 1.7, it's considered ionic. But in this mid-range, anywhere between 1.7 and 0.4, then it's polar covalent bonds. And those are going to have a major impact on the properties of your substance, whether it's nonpolar, polar, or ionic. So keep that in mind as we continue to study the way matter interacts with other matter. We'll see you soon.